Hello my dear students. Today we'll speak about how to measure the different elements potentials in reference to the standard hydrogen electrode. How we use the standard hydrogen electrode to measure the different electrode potentials. For example, we will take zinc as an example of this and copper. The first is zinc. How can we measure the zinc potential? By forming the galvanic cell from a standard zinc half cell and a standard hydrogen half cell. So, what is the standard zinc half cell? It is a zinc sheet dipped partially in a zinc solution with the molarity of the ion concentration of zinc equals 1 molar, and the standard hydrogen electrode, a platinum sheet here with a surface area 1 centimeter square and dipped in a solution, contains hydrogen ions with a concentration 1 molar, and flow on this platinum sheet hydrogen gas with partial pressure 1 atmospheric pressure. So what will happen when you connect the two electrodes, the standard zinc electrode with the standard hydrogen electrode, and connect between them with a voltmeter? It is a galvanic cell. It will produce a spontaneous it will produce an electric current, or a spontaneous oxidation reaction will happen between zinc and hydrogen electrode. So in this case, zinc is more active than hydrogen. So the voltmeter reading is 0.76 volts, and its pointer indicates that the electrons flow from zinc electrode to the hydrogen electrode. So the electron here flow from zinc electrode to hydrogen electrode. It means that the zinc electrode acts as anode and the hydrogen electrode, standard hydrogen electrode, acts as cathode. Okay? Electrode, which means that zinc electrode acts as anode and hydrogen electrode acts as cathode. So how can we calculate the potential of zinc in this case? Now the electromotive force equals the standard oxidation potential of the anode plus the standard reduction potential of the cathode. So the electromotive force equals the standard oxidation potential of zinc zero solid plus the standard reduction potential of hydrogen ion. As the hydrogen ion standard reduction potential equals 0, then it is cancelled from this equation, and the electromotive force here equals the oxidation potential of zinc. So the electromotive force, or the oxidation potential of zinc as anode, equals the electromotive force equals positive 0.76 volt, and it refers to the oxidation process that happened to the zinc zero solid to give oxidized from zinc zero solid into zinc positive 2 ions and release 2 electrons. So the standard oxidation potential of zinc zero solid equals positive 0.76 volt. So we want to calculate the standard reduction potential of the same electrode, as the standard reduction potential of zinc positive 2 aqueous equals negative the standard oxidation potential of zinc zero solid, then the standard reduction potential of zinc positive 2 equals minus 0.76 volt, and it refers to the reduction process when it happens to the zinc positive 2 aqueous, when it takes electrons and transform it into zinc 0 solid, and the standard reduction potential here equals negative or minus 0.76 volt. So this is how we can calculate the zinc oxidation potential, and the reduction potential of zinc ions by using the standard hydrogen electrode as a cathode. So how can we measure another element? For example, the copper electrode. How we can measure the copper electrode potential? Using the standard hydrogen electrode SHE by forming galvanic cell from standard copper electrode or a standard copper half cell and a standard hydrogen half cell. So standard hydrogen half cell composed of a sheet of platinum 1 centimeter square dipped in a solution with a concentration of hydrogen ions in it equals 1 molar, flow over it a gas, hydrogen gas, flow in this platinum sheet which is covered by a spongy black finely divided platinum, okay, to absorb hydrogen gas. Okay, and the standard copper electrode, it is a copper sheet dipped partially in a copper solution with a concentration of 1 molar. Okay, we connect between them by an electric wire and voltmeter. So the pointer of the voltmeter indicates that the electrons flow from hydrogen to copper electrode. In this case, as electrons go from standard hydrogen electrode act as anode, and the standard copper electrode act as cathode. So how can we measure the electromotive force in this case? The electromotive force equals the oxidation of the anode, the standard oxidation potential of the anode plus the standard reduction potential of the cathode. So the electromotive force equals the standard oxidation of hydrogen gas plus the standard reduction potential of copper positive 2. And as the standard oxidation potential of hydrogen equals 0, then the electromotive force here, which equals positive 0.34, equals the reduction potential of copper electrode, and it refers to the copper positive 2 ion when it takes 2 electrons and reduced into copper 0 solid. This is the standard reduction potential of copper positive 0.34 volt. What is the oxidation potential of copper? As the oxidation potential of copper equals minus the reduction potential of copper ion, then the oxidation potential of copper 0 solid equals negative or minus 0.34 volt, and it refers to the oxidation process when it happened to the copper 0 solid oxidized into copper positive 2 ion and releasing 2 electrons, and the oxidation potential of it is minus the reduction potential of the same electrode. It equals negative or minus 0.34 volt. We take an example of this. If the cell diagram of a galvanic cell represented by the following: 2 lithium 0 solid oxidized to 2 lithium ions, and here the salt bridge, the cathode is reduced from hydrogen ion into hydrogen gas 0. So determine the cathode in this cell ions. So we write the cell diagram by anode first and its 2 oxidation state, separating between them with 1 diagonal line, and 2 diagonal lines represents the salt bridge and the cathode, and the 2 oxidation state of the cathode, the higher oxidation state and the reduction state of the cathode. So the cathode here refers to the standard hydrogen electrode. The oxidizing agent. Oxidizing agent is the agent that oxidize other substance, take electrons from another substance. So the oxidizing agent here is the hydrogen ions which take electrons from lithium electrode and transfer it into lithium ion. So hydrogen electrode here, or hydrogen ions, is the oxidizing agent in this reaction. So the third point, the oxidation potential. Calculate the oxidation potential of lithium, knowing that the electromotive force of the cell equals 3.04 volt. In this case, the electromotive force equals the oxidation potential of the anode plus the reduction potential of the cathode. But the reduction potential of the cathode equals 0, as it is a standard hydrogen electrode. So the electromotive force here equals the standard oxidation potential of the anode. So the standard oxidation potential of lithium equals the electromotive force of the cell, which equals positive 3.04 volt. Another question. Look here, a galvanic cell represented by the equation 2m positive aqueous, 2m positive aqueous with hydrogen gives 2m0 solid with 2 hydrogen ions. The electromotive force of this process equals positive 0.8 volt. So what is the standard oxidation potential of the electrode M? We have to notice that what happened here in the M electrode is the reduction. So electromotive force here refers to the reduction of M electrode from positive 1 as a charge to 0. So here, as the standard oxidation potential of hydrogen electrode equals 0, and the electromotive force of the cell equals the standard oxidation potential of hydrogen as anode plus the standard reduction potential of M as cathode, and the standard hydrogen electrode potential oxidation reduction equals 0, then the electromotive force of the cell equals the standard reduction potential of the cathode. Okay, but here he asks about the oxidation potential of the electrode M, and it equals negative this value, as the reduction potential of M as the cathode equals positive 0.8. So the oxidation potential of the same electrode M equals negative 0.8 volt. And at this point we finish our session today. Thank you.